Yes.
You could just go to slideshow and click, go up to the top, see slideshow.
Yes.
There, and then,
Yeah, this.
and then just, there you go.
Okay, great. That works perfect. Thank you. Okay, thanks. So, hi everyone. So I was told that this should be a public talk for a somewhat more general audience because it's part of my PhD defense. Then somehow this public talk ended up being given to a room full of experts. So here we are. So let's see how that kind of goes to mix and match both sets of people. So to kind of keep everyone happy, I'm sort of just going to give maybe a slightly more general overview of some results on things I've worked on instead of getting into too many technical details. So the work I'm going to talk about, as you can sort of see from the title, is based on separation of variables from wave functions to correlators in high-rank integrable spin chains. And this particular work is based on work with Dima Volin, Nikolai Gromov, and Fedor Levkovich-Masliuk. And also, just because this is part of my PhD defense, let me take this moment to thank all of my collaborators on all the projects I've worked on. So Maria Silou, who's one of my supervisors, Chiara Paletta, Anton Pribitok, Anna Rator, Nikolai Gromov, Sebastian Aron, Fedor Levkovich-Masliuk, and Dima Volin, who's my second supervisor. So thank you to all of you. Okay, so on to business. So I guess the motivation for most of us here is to solve 4D quantum field theory. Okay, and that's roughly what all of us are trying to do in some shape or form or another. And in the special case of n equals 4 super Yang-Mills, which is of course dual to type 2b strings and ADS5 cross S5, we have special help in the fact that this theory is an integrable system. Okay, and this integrability manifests itself in various different ways. So at one loop, it was discovered in 2002 by Minahin and Zarembo that the dilatation operator in the SU2 sector and the SO6 sector could be mapped to the Hamiltonian of an integrable spin chain. And this allows you to use various techniques from the integrability toolbox, beta ansatz, and so on, to essentially diagonalize the spectral problem. In the non-perturbative regime, we still have integrability, and here it takes the form of the quantum spectral curve, which is ultimately a Q system of the type appearing in integrable spin chains, but with novel analytic requirements. And this quantum spectral curve is really the ultimate solution of the n equals 4 spectral problem and has led to many, many, many nice results. So in particular, it has been used as a perturbative tool, for example, to calculate scaling dimensions to very high orders in the coupling constant. It's also been used to get very nice numerical results and has also been extended to various other theories. For example, the eta deformed ADS5, similar to what Fiona was talking about a few days ago, and also for the ABGM model. So this is all well and good. So what we can really say from this is that we know quite a lot about the scaling dimensions of local operators in n equals 4 super Yang-Mills using quantum spectral curve. On the other hand, n equals 4 super Yang-Mills is a conformal field theory. So to say that we've really solved it, we also need to be able to write down 3-point structure constants. So quantum spectral curve, if it knows about every state in the theory, it should also know about wave functions and hence correlation functions. So how can we exploit quantum spectral curve to make any kind of nice statements about correlation functions? And there was one very nice example where this was really sort of put on firm footing, which was an example of a cusped Wilson loop in n equals 4 super Yang-Mills in the so-called ladders limit, where this type of thing was really done explicitly. So this is a 3-point structure constant written in terms of the Q functions appearing in quantum spectral curve. And the result takes a form which is very, very similar to what one sees in integrable spin chains expressed in what are called Sklinen's separated variables. Unfortunately, this separation of variables procedure in integrable spin chains has really only been developed rigorously for SL2, at least before I started my PhD. And of course, we need PSU 2,2/4 to describe n equals 4 super Yang-Mills. So there's two challenges here. First, we need to know how to extend this construction for higher rank algebras and also for supersymmetric algebras. So, okay, so our goal with all this in mind would be to somehow separate variables in n equals 4 super Yang-Mills, which sounds like quite a big undertaking. So admittedly today, we're going to be a little bit more modest. And what I'm actually going to describe to you is how to separate variables in high rank integrable spin chains, which of course includes either finding wave functions in a factorized separated variable basis, and also how to actually efficiently compute observables using this technology. So what we find are the following, just a quick overview of the stuff we find. So for SUN spin chains in any compact representation, we have the following explicit form of the wave function expressed in terms of separated variable coordinate x's. So the wave function takes the form of a very, very simple factorized determinant where you have a product over so-called one particle wave functions. And obviously it's very, very simple and much more simpler than the types of expressions which you would get from doing, for example, the nested beta. So this is only one part of the story. So we know the form of the wave functions, but we also need to know the domain in which these variables live. So what is the set of coordinates? What range of values can these coordinates x take? And so this has been done by linking this problem to the representation theory of GLN, which makes everything very nice and very clear. So what we have found is that the coordinates, the separated coordinates, can actually be parameterized by what are called Gilpin-Safelin patterns, which are very interesting representation theoretic tools and counting objects in which appear a lot in combinatorics, and they're roughly similar to semi-standard Young tableau. And as well as this, we have also managed to find very simple expressions for scalar products and form factors for both SUN, so compact, and also non-compact SLN spin chains as very, very simple determinants in Baxter Q functions of precisely the type which you would get in using quantum spectral curve at n equals 4 superangles. Okay, so that's sort of like the rough idea of what we have. So to kind of outline how the rest of the talk is going to go. So first of all, I'm just going to give a quick overview, and it's mostly review since I know the vast majority of people here have heard me speak about this on at least one or two occasions in the past. So I'll review what we know about the construction of the factorized wave functions, and then move on to some more newer stuff, which involves the computation of the SOV measure. So this roughly means computing scalar products using separated variables, and also how this technology can be used to compute other observables such as form factors. And then of course, I'll end with some recap and outlook. Okay, so SOV wave functions. What is the structure of these factorized wave functions and how do we get there? So I'll start with a quick review of the work of Skleinen on separation of variables in SL2 spin chains. So as usual, we start with our monodromy matrix with operators A, B, C, and D. And if we follow the techniques of the algebraic beta ansatz, then of course we can construct the eigenvectors of the transfer matrix and the Hamiltonian and conserved charges in this very simple way by acting on our vacuum state with our B operator evaluated at beta roots. And these beta roots can be packaged inside this Baxter polynomial, which is the product over all beta roots of U minus beta root. So the idea behind separation of variables is that if we can somehow diagonalize this B operator, which is a polynomial, so it has operator valued roots, then the basis which diagonalizes these operators is immediately going to serve to factorize our wave functions, because a very simple rewriting of this expression using the Baxter Q function just tells us that the wave function in its basis factorizes into a very, very simple product of simple one-dimensional factors, which is kind of what we mean by separation of variables, right? So the wave function has factorized into a product of sort of one-dimensional factors. So that's SL2. This has been kind of known for a very long time. So it's only been very recently when people have started to make progress for the higher rank case. So the higher rank case was initiated by Skleinen in 1992, who worked on the SL3 problem. So now the monodromy matrix is 3 by 3. So we have T11, T12, T13, and so on. And the B operator is no longer just simply T12 like it was in the rank 1 case, but is now a much, much more complicated operator. Nevertheless, in the classical limit of the spin chain, this indeed produces separated coordinates, which can be shown very, very nicely. But it's not clear how this construction actually works in the quantum case. How do we use this object to factorize wave functions? And it wasn't until 2016 where this was actually first noticed in a paper by Kolyagramov, Fedor, Levkovich, Masliuk, and Grigoriy Sizov, where they showed that this B operator could actually be used in a very similar spirit to what was done with the SU2 algebraic beta ansatz and construct states by just simply acting with this B operator on the vacuum evaluated at beta roots. And again, Q1 is just the usual Baxter polynomial. So this was actually proved that this actually really works for all states for SU3 in a paper by Lyashuk and Slavnov in 2018, and later by myself and Dima Volin for the compact SUN case in 2018, and by myself, Fedor, and Kolya for non-compact SLN last year. And the idea for the construction of the separated variables is again very simple. The idea is to take the operator roots of B and consider those to be your separated coordinates. And again, in the basis, which diagonalizes this B operator, the wave functions are again going to factorize into a very simple product of Q functions. And this is roughly how the story goes for the defining representation of SUN and for its symmetric powers. But the generalization to any representation of SUN is very, very simple. And it just means that the wave functions, instead of being a simple product of Q functions, become very, very simple determinants in Q functions. And similarly, the SOV basis is given by diagonalizing spline B operator, which is also very often referred to as B good in this community. Okay, so what exactly can we say? So as I said, the spectrum of these separated variables is governed by representation theory of GLN, which is in this case described by Gelfand-Seyfert patterns. So what is a Gelfand-Seyfert pattern? Because I know maybe not many people are familiar with these. So a Gelfand-Seyfert pattern just means take your highest weights of your representation. So in this case, lambda 1 alpha, lambda 2 alpha, lambda 3 alpha, and lambda 4 alpha, if I look at GL4, and fill up this triangular way with numbers. So I have x11, x21, x31, and so on. And the requirement for this to describe a state just means that I have certain branching rules, which tells me that this number must be between this number and this number. This number must be between this number and this number. This number is between this number and this number, and so on. So if we look at an example of the defining representation of, say, SU3, then we have something like this. So we have lambda 1, lambda 2, and lambda 3 will be equal to 1, 0, 0. And we just fill up these arrays in all possible ways. And these describe the three states of the representation. And so we also see that for this particular class of representations, this number was actually fixed to 0, even though in general it need not be. And in this case, we say that this number is actually non-dynamical. And this corresponds to having one separated variable also take non-dynamical values, which doesn't change from state to state. And what's very nice is that these non-dynamical parts actually decouple from the overall wave function. And this is what leads us from starting with this determinant type expression down to simple products of Q functions for simple representations. So for example, if we look at the defining representation of SU3, we just get a simple product of two Q functions. Whereas if we look at the anti-fundamental representation of SU3, we just get a single simple 2 by 2 determinant in Q functions. Okay. So what we've kind of understood, and from what I've kind of reviewed, is that the wave functions for the higher rank spin chains are actually now very well understood. But of course, the story doesn't end with wave functions. We really want to understand correlation functions, form factors, and various other observables. So the simplest possible way to start here is actually the scalar product between the wave functions into separated variable basis. So we want to consider the overlap of two transfer matrix eigenstates written in terms of the wave functions in the SOV basis. So the scalar product will include some measure factor here, this SOV measure. And the problem which actually makes this a bit complicated is that this measure need not actually be described by a diagonal matrix. So for the simple case of rank 1, so SU2, this is actually diagonal, but the kind of key feature which arises when you go to higher rank is that this is no longer diagonal. And ultimately, this actually makes things a bit difficult because if you imagine that this, this matrix gives you the overlaps of X's and Y's at two different possible SOV bases, then you have to do some work to actually compute these matrix elements, which need not actually be very easy. So what I'm going to do now is to describe a simpler method for actually computing this thing without needing to calculate the matrix, the measure elements explicitly, and in a way which can actually be generalized to non-highest weight representations and even models closely related to ADS-CFT, which is what we're ultimately interested in. Okay, so I'm going to describe how to compute the SOV measure using sort of more modern functional techniques instead of the more traditional algebraic techniques for this. So the main idea for this, or the main sort of input we use and motivation, is this property of orthogonality. That if we take two transfer matrix eigenstates, say psi A and psi B, then assuming the transfer matrix and conserved charges have non-degenerate spectrum, then this should just be proportional to some product or delta. All right. On the other hand, the wave functions we know are completely fixed in terms of the Baxter Q functions. So how can we reformulate this property of orthogonality using Q functions? And this is a notion which we refer to as functional orthogonality. So to mention a little bit on the chronology of how this approach actually came about. So this was actually originally used in a direct quantum field theory setting in using this example of the Cusp-Wilson loop in n equals 4 super Yang-Mills and the latter's limit, and was then later, only then later eventually developed for non-compact SLN spin -1/2 spin chains. And then finally, a functional and operatorial approach were combined together for compact SUN spin chains and non-compact SLN spin chains. So somehow it was actually developed in a QFT setting first before being later constructed in spin chain setting. Okay, so how does this work? So the key object we use is the Baxter equation. So the Baxter equation links the transfer matrix eigenstate and the associated Q function together with certain coefficient functions, so Q theta, in a simple way. And this Baxter equation can be rewritten as the action of some finite difference acting on a Q function. So Baxter's equation just becomes O times Q1 is equal to 0. And the key input, which allows us to formulate this functional orthogonality relations, is that there exists a sort of bracket, which I'll define in a moment, for which this operator O is self-adjoint. So this bracket has the following form. It's defined by bracket f as being the integral of du times some measure factor mu times my function. And if you impose that this operator O is self-adjoint, you actually get some restrictions on the measure. You find that it has to be this very simple 1 over Q theta times Q theta with some shift times some I periodic function, which for the moment I've just set equal to 1. So provided I choose this measure factor to be this thing, then this operator O will be self-adjoint with respect to this bracket. And it's this observation which allows us to formulate this notion of functional orthogonality. And to proceed, the idea is that we don't actually have one possible such measure. As I said, we can multiply this by any periodic function. So we actually have available L such measures, so one for each side of the spin chain, of the following form. So I replace mu with mu alpha, and these mu's are chosen just to be my previous mu times some I periodic function rho. And the explicit form doesn't matter, but what we ultimately look at is inside this bracket, we put an OA minus an OB. So this finite difference operator O depends on the state in question by virtue of the fact that it depends on the transfer matrix. So if I look at OA, I mean the transfer matrix eigenvalue associated to state A. And if I look at OB, I mean the transfer matrix eigenstate or eigenvalue associated to my state B. Okay. And you can see that these Q theta terms obviously don't care about the different state in question. So when I look at OA, where is it? OA minus OB, the only difference in these expressions comes from the transfer matrix eigenvalue. So if I expand my transfer matrix into a basis of integrals of motion, then there's only these things which are going to contribute. The leading term is identity. So if I look at two different states and take the difference, this term is of course going to vanish. And what I'm ultimately going to be left with is a sum of terms like this. So IA minus IB with subscript K, and I sum over K from 1 to L times this coefficient function here, which is just u to the K minus 1 QA QB over some Q theta factors sandwiched inside this bracket operation. And the idea that we proceed with is that these differences of integrals of motion must be non-zero for at least some state, assuming the transfer matrix eigenvalues are non-degenerate. So in order for these things to be non-zero for at least one state, and for this linear system to have a non-trivial solution, it means that the determinant of this linear system must actually vanish. So what this means is that for any two states, A and B, we must have that the determinant of this object is equal to 0. For any states which A and B which are not equal. So this means that this is a very natural notion of a scalar product, right? So we want our scalar product to give 0 for two different states, and now we've constructed something involving Q functions, which indeed gives 0 for two different states, and can actually be checked to give something non-zero for the same state. So this thing seems to very, very closely match the structure of the scalar product, or what it would look like in separated variables. And this notion can actually be extended very, very easily to the higher rank case, and it follows basically the exact same procedure. So for the higher rank case, the idea is that we have the SU3 Baxter equation. So in this case, there are actually two Baxter equations. There's a Baxter equation which annihilates Q1, and also the dual Baxter equation which annihilates the auxiliary Baxter functions. Okay, so this Q1 is the momentum carrying beta roots, and these Q upper 2 and Q upper 3 are the auxiliary, carries the auxiliary beta roots. And now it is no longer the case that this thing is self-conjugate, but actually these two Baxter operators are conjugate to each other under this bracket operation, which I wrote down before. So the whole thing actually can generalize very, very easily to higher ranks. So SL3, SL4, SLN, absolutely no problem. And as before, we take the overlap of two different states to be equal to, or to be proportional to delta AB. And this gives us another linear or determinant of Q functions, which must be again proportional to delta AB for two different states, A and B. So this is a very natural notion of scalar product for higher rank spin chains. Okay, so now we can ask ourselves, what is the corresponding operator construction? So we can try to extract the SOV measure from this integral representation. So if we write out this, determinant and evaluate these integrals by residues, what we ultimately find are something of this form. So we're going to have sum over pairs of values x and y, and then this simple type of determinant in Q functions times this simple product of Q functions. And you might recognize this simple product of Q functions as being exactly the type of thing we had earlier when we diagonalized Linen's B operator, because these corresponded to the wave functions of the transfer matrix. So these are the right wave functions, and somehow these must correspond to the left wave functions. So how does this work? So as I said, this matches what we get from B, and we don't really understand what this is. So the idea is to assume that these correspond to the wave functions in an eigenbasis given by some new operator, which we call C. So the C operator we introduced in a paper in 2019 with Kolya, Feder, and Dima. So what is this C operator? Well, it's actually very closely related to the B operator. So if you write out the B operator explicitly in component form, it's actually quite a big mess. But remarkably, this C operator, which gives us our left SOV basis, is actually very closely related. The only differences appear in the shifts of the spectral parameters in certain terms. So what you might like is that this thing is the Hermitian conjugate of this thing, because when you do the SU2 beta ansatz, for example, you have a C operator, you have a B operator, and they're related under Hermitian conjugation. But actually, this doesn't work for the higher rank case. And the reason is that Hermitian conjugation actually doesn't work very well for higher rank spin chains. So for the SU2 case, everything is nice, and we can map all our TIJs to TJI under Hermitian conjugation. But for higher rank, we actually have problems. So the idea is that what we actually need is a new type of operation, which we call star, and was introduced in a paper with myself, Kolya, and Feder, which is an anti-automorphism. So it swaps the order of generators and acts on Tij of u by giving us Tij of minus u. And you might think that this is a sort of trivial operation, since all I do is swap u to minus u, but the non-trivial part actually comes from the fact that I have to swap any two operators I act on as well. Okay, and actually what we managed to show is that the image of B under this map actually gives us C. And this can actually be taken as a definition of C. So we define C to be the object given by acting on B with this star operation. And in some previous works, we were able to develop some tools for studying the diagonalization of this B operator. And because we have access to this star map, all of these tools carry over directly from B to C, which makes the whole thing actually quite nice. Okay. Okay, so yes, so in this basis which diagonalizes the C operator, the left wave functions now actually take a very simple form of a single determinant, and we can compute the overlap by summing over all SOV states and computing the measure directly. And what we find is that this technique perfectly matches what we get from this functional integral approach, which I mentioned earlier. So we have two approaches to SOV. We have this operator approach, which involves diagonalizing this B operator and this C operator. And we also have this functional approach, which involves this functional orthogonality and this finite difference operator O and this bracket operation. And these two approaches perfectly coincide. Okay, so what we kind of get from this, oh yeah, and actually just to give a quick example. So unlike in the SU2 case, the measure in this SOV basis is actually non-diagonal. So we have a set of SOV basis Y and an SOV basis X, and this matrix M corresponds to their overlaps, but this matrix M is actually not diagonal in contrast to the SU2 case. Still, it's actually very, very simple and just has this very simple block structure. So this is for SL3 length 2 with some generic spin S, so non-complex spin chain. Okay. Discuss scalar. I'm going to move to some more in fact. And you can, of course, type by matrix elements of the set and explicitly the action on this writing out the functions overlap with the function. This so the start again the Baxter equation. So we can, since it's pretty sufficient for depending how this some parameter can be any what it's. So what this means is that you can actually take QA with your operator. Sorry, what's your question? Okay, so you can take the Baxter equation just means that you can put O inside here and you will get 0. But actually what you get from doing this variation is that you can also put a derivative of this operator O inside here and act on Q1 and you're still going to get 0. Okay, and this is actually very powerful because if you work out what this derivative acting on O is explicitly, okay, so if P might be an inhomogeneity, so you're going to get some derivative with respect to Q theta, but also a derivative acting on the transfer matrix and the integrals of motion. And the derivative on the transfer matrix takes this very simple form. So here you get the derivative acting on these independent integrals of motion. And unlike in the previous case, where we had the scalar product, you are now going to get an inhomogeneous linear system for the derivative of these integrals of motion, which you can actually solve as a determinant. So immediately you can express the form factors of these quantities in terms of very simple determinant of Q functions. So what we've succeeded in doing is constructing a sort of prototype of observables for which we can really write down what would correspond to 3-point functions n equals 4 super Yang-Mills as determinant in Q functions. And this has actually also been generalized to the case of conformal fishnet theory and fish chain, where this can really be done in a sort of QFT type model. Okay, so there's also a very, very interesting quantity we have access to using these methods, which is the following. So what this quantity is the overlap of a left transfer matrix eigenstate constructed with a twist G tilde and acting on a right transfer matrix eigenstate constructed with a twist G. So this is almost like a scalar product between two different transfer matrix eigenstates, but now the left and right state are constructed with two different twists. So this might seem like a little bit of a weird quantity. Usually we're interested in really scalar products of transfer matrix eigenstates. So why do we care about this thing? And the reason actually comes from, again, looking at conformal fishnet theory and fish chain. So in this case, you're looking at the scalar product, which is your conformally invariant scalar product. And for these principal series representations, which you're interested in, the scalar product is actually divergent. So as soon as you try to take some physical conformal field theory model like this and compute this overlap, for the case where both eigenstates are constructed with the same twist, you're actually going to get some divergent expression. But actually, if you construct these things with two separate twists, you will actually get a finite result. So considering different twists actually provides a very, very natural regularization procedure for computing this type of thing. Of course, you can compute this, you can remove the divergent part and read off some finite expression. So the key kind of thing which allows us to do this is based on an observation in the work by myself and Dima, where we show that for a special choice of the twist, the SOP bases are actually independent of the twist. Okay, so this means that the SOP basis will actually serve to factorize transfer matrix eigenstates built using any twist you like. Okay, you can have all twist eigenvalues set to 0 if you want, everything will still work. So I can insert a resolution of the identity between these two vectors, and both the left state and the right state will factorize into products of Q functions. But we know how to rewrite this thing using this integral approach, which I discussed. So of course, we can just immediately rewrite this overlap between two different twisted transfer matrix eigenstates as a very simple determinant in Q functions. And this approach, or this type of quantity, was actually also recently considered in a paper by Samuel Belliard and Nikita Slavnov a couple of weeks ago, actually, where they also tried to compute this type of overlap using nested beta ansatz technique. But of course, you have to do quite a bit of work there, whereas in our approach using SOV, this type of quantity appears to come naturally. And we can actually look at some very, very simple examples where you can do all of this explicitly. So for example, if you look at a non-compact SL3 spin chain of length 1, where the Hilbert space is just given by polynomials in 2 variables, then you can really write down, for example, if you take 2 twisted vacuum states, the highest weight states of the spin chain, you can really write down their overlap explicitly, write down the Q functions explicitly, which are just given by simple exponential type things, and then calculate the integrals, which I mentioned earlier, appearing in these bracket operations, and write down the scalar product. And of course, everything works perfectly. Okay, and so that's sort of like the main idea and the main power of this. And this approach was actually also used again recently in a paper by Andrea Cavaglia, Nikolai Gromov, and Feather, Levkovich, Masliuk, where they applied all of these techniques to the conformal fish chain, which is holographically dual to conformal fish net theory, and showed how all of these things can also be generalized in that case, even in the absence of highest weight. All right, so yeah, so again, since it's a public talk, I was told to keep it maybe a bit shorter than some of the other talks. So I think I'll finish by recapping what we've talked about and discussing some future directions for research. So the first thing we have is these very simple factorized expressions for the wave functions in an SUN spin chain, which are given by very simple determinant expressions in Q functions. Okay, so these one particle wave functions couldn't be nicer. Just very simple determinants, unlike what you would get in the nested beta ansatz. All right. We also were able to identify the spectrum of the separated variables with the representation theory of GLN and use those techniques to make many statements about the spectrum of the separated variables. And also we were able to use these functional orthogonality relations to be able to write down very simple expressions for scalar products and form factors as determinants in Q functions for both compact SUN and non-compact SLN spin chains. All right. So moving on to what we can do in the future, the obvious thing we need to do is to look at supersymmetric SUM/N spin chains, and some first steps in this direction were taken by Maillet, Nicoli, and Vignoli in a paper about 2 years ago, where they constructed an SOV basis for the defining representation of SUM/N. So the natural thing to do would be to look at representations beyond the defining representation. And so for this, of course, we use this technology of Gelfand-Seyfert patterns quite a bit in our story. So the next obvious step one would need to do is construct a supersymmetric Yangian version of Gelfand-Seyfert patterns, which is currently work in progress with myself, Sebastian Yaron, and Dima Volin. The next thing involves explicitly applying this stuff to 4D conformal field theory, in particular the duality between the 4D fishnet and fish chain duality, which of course really corresponds to an exactly solvable 4D QFT. And it was shown in their recent paper that this functional SOV approach actually works perfectly. And is related actually to the work of Derkachov and Olaguchi, who have also been constructing separated variables for this model, but in a sort of different regime. And finally, let me comment about the Godan model, which has attracted a lot of attention recently. So the Godan model appears as a special semi-classical limit of the XXX spin chain, and it was shown recently in a series of papers by Burish, Lacroix, Mann, Quintavella, and Volko Shimiris that the wave functions of the Godan model actually coincide with conformal blocks of 5-point functions that appear in 5-point functions in conformal field theory. Yeah, so there's, I guess, a lot to do in the future, and it would definitely be interesting to come back to a lot of these questions. All right, so yeah, I'll finish up there with a sort of shorter talk. So thank you very much.
Thank you, Paul. Are there any questions? Well, I have a question myself. So you've been applying this to mainly SUN type things, but could you also do SON or maybe even exceptional Lie groups or Lie algebras?
So the answer to that is not at the moment not particularly clear. So the problem is that the problem essentially resolves around the Baxter equation. So for this SUN case, we just use the standard Baxter equation. For even if you go to the supersymmetric case, it's clear that using the standard Baxter equation actually doesn't work and actually doesn't do the job for what you need to do, this functional orthogonality relations. So it's clear that you need to sort of understand the Baxter equation in a sort of different light. So there's already been work on the SON Baxter equation. Actually, a paper a long time ago by Geneva, where they looked at a generating function for essentially a sort of a slightly different version of the Baxter equation for SON spin chains. So Dima will be talking about the SON Q system and related works in the next talk. So hopefully what they're doing as well will be able to push this a little bit more and eventually get SON. So at the moment, the conclusion is, yeah, SON doesn't work immediately, but I would say it's not very far away.
Okay, thanks. So
Okay,
Charlotte, you have a question?
Yeah,
Yes, I think I probably asked before, but it seems you do not have access to the norm itself. Can you explain exactly why?
Right. So indeed. So the problem with the norm is that, okay, so first of all, this works without imposing any reality conditions on the spin chain. So if you want to get a norm or something like this, immediately you need to impose certain things, right? If you have twists, you want them to probably be phases. If you probably also want like this parameter h bar to be equal to I or something like that, you have and inhomogeneities to be real. Okay. So first of all, what we've done here works without imposing any reality conditions. But as regards to actually computing the norm, the problem is that the Q functions and the separated variables do not behave very well under Hermitian conjugation. So this expression which we have, if I go all the way back to the beginning. This is the simplest higher end case where the wave functions just take this simple product of Q functions. So if you wanted to take Hermitian conjugation of this thing, you would need to know how the separated variables transform under conjugation. All right. But this is not a very easy thing to do because it involves you would need to know how this B operator transforms under Hermitian conjugation, which is a much more complicated object than you have in just SU2. And I mean, that's essentially what it boils down to. The separated variables don't behave well under conjugation. So all we have access to, the scalar product which we have access to involves the action of a left transfer matrix eigenstate on a right transfer matrix eigenstate, which are normalized in very particular ways. So I guess the main point is that we don't actually have access to the norm itself, but for physical quantities, it actually doesn't matter. So if I go back to what I was saying about form factors, so if you solve this linear system for these form factors, the result is that normalization of the left and right states will actually drop out. So provided you're not interested in the norm, but in the like this kind of normalized form factors, then it doesn't matter whether you use the norm itself or the type of scalar product we consider. So I guess it depends on what you're looking for. I mean, if you want something like, I mean, I guess these examples you have with defect conformal field theory, you really need access to the norm.
Some nice rewritings of the Godan determinant or something like that could be interesting.
Yeah. So
this case where you have two different twists, it does not involve the norm in any limit or anything.
It may actually be possible to reduce the norm in some sense. Although with these two different twists, we need a very particular form of the spin chain, like the twist matrix has to be a very particular form. So if you take, it's sort of very like off diagonal. So as soon as you try to take, you can't take or consider a case where these things are actually diagonal. In this case, while one of these will become a usual transfer matrix eigenstate, after you rotate back, this thing will actually give you some mess and will just be something a bit different because the rotation will act differently on these things. So norm is not really a good quantity from this approach, but well, normalized form factors work out perfectly fine.
Okay, yeah, thank you.
Any other questions?
Yeah, maybe a quick one. Paul can speak too loud, but sorry. How far, if you know this argument is taken, and how does it relate to you regarding this XXX Godan argument for the wave function? Is it overlap to a 5-point conformal block, or there is something more?
Sorry, could you repeat, please, Anton?
Yeah. So the wave function, as you said, in the Godan model regarding the XXX, this is just wave function which is related to the conformal blocks, or there is something more now? Like from your perspective, can you find higher or lower point functions for these models in terms of overlaps?
Yes, that's a great question. So actually, so anytime I have heard any of these authors speak, I have asked them precisely the same question. And the conclusion from what I've heard so far appears to be no, that it's really just the wave function equals conformal blocks. And so I also asked them if they have interpretations for other quantities in the Godan model, like you say, so some overlap or some form factor or something like this. And the conclusion seems to be so far, the answer is no.
Okay, yeah, thanks.
Okay, thank you. So if there are no further questions, let's. You, Charlotte? Yes.
One question.
Go ahead.
What about the descendant states? Can you also get a overlap of descendant states? I guess all your states are highest weight.
Yeah, exactly. So I have generic twists. So in principle, every state is highest weight.
Okay. Yeah.
Okay.
Actually, sorry, can I just ask a quick question too? Do you know the formulas you have? Is it easy to take like a continuum limit, like to say try and match with the string theory or something like this, right?
Yes. So great question. I've tried and did not have much luck, I have to say. So, I mean, even if you don't want to look, I mean, if you just want to do something simple, like say take like finite temperature limit or thermodynamic limit or something like this. Even in this case, it's not so tricky. So, I mean, if you start from this expression like this for the scalar product or even some normalized thing, the problem is that in this case, like this integral operation will involve then taking an infinite number of residues. And this tends to get a bit messy. So I've tried looking at the homogeneous case, which is a bit more relevant in that case, which in this case, all of these, so for this case, like these are just simple poles that are inhomogeneity and inhomogeneity shifted. And if you go to the homogeneous case, then you just have, say, u to the L and u plus I to the L, something like this. But of course, if you send L to infinity, then this becomes not very meaningful because, I mean, the poles become of infinite degree.
I see.
So for the moment, I don't really have an answer to this. If it's possible, I suspect it definitely is possible. But I mean, comparing with string theory at the moment is probably one of the harder things. So I think if one wants to try looking at the continuum limit.
Небольшая онлайн такая конференция, я Диму хотел Волина.
Was that a question? Or
no, I think it was just background noise.
Okay. So I think definitely this needs to be done because there are a lot of things where this is actually necessary. So I mean, for ADS-CFT, right? Okay. If we look at trying to do all this for quantum spectral curve, really at in ADS-CFT, right? So one thing we could look at first is the Hubbard model, right? So the Hubbard model at finite temperature, the quantum spectral curve bears a lot of like resemblance to the quantum spectral curve for ADS-5 process 5. It's very similar. It's just instead of being on an H-sheet Riemann surface, I think it's a 2-sheet Riemann surface. But this involves going to finite temperature. But so of course, like, being able to do these things in sort of like this infinite volume of infinite number of degrees of freedom needs to be done.
Okay. Yep.
Okay. Thank you. If there are no further questions, let's thank Paul again. Thanks, Paul. Okay, so the next talk, sorry, will be in start at 3:05. So there's a coffee break for now for who wants. And as I said, because this is part of Paul's defense, we'll now I would now like to give the word to the chairman of the defense committee because Paul had his defense this morning. So Tristan,
maybe I'll just suggest return